All right, you guys, so we're going to finish our discussion of solubility and pH. And so I'm just going to start at the beginning and kind of rehash some of the things we spoke about yesterday, just to get that fresh in your mind, and then we'll go through and finish the rest of these notes. When you're finished with these notes, you're going to be working on the pre-lab for the lab that we'll be doing on Thursday. So we said that water is called a universal solvent because it dissolves so many different substances. And water molecules are polar, which allows them to interact with other polar substances and dissolve them. We recalled that ionic compounds are essentially just very polar compounds. So anything that's this way on the chart, so polar, covalent, and ionic compounds are really susceptible to being dissolved by water because of its polarity. Nonpolar covalent compounds cannot be dissolved by water. So we looked at these pictures to compare how ionic compounds dissolved in water versus how polar covalent compounds dissolved. And we considered the little deltas on our polar covalent molecule right here. We thought about what was similar between images A and B. So they both have water. The water is forming little circles kind of around the other particles that they're dissolving. And the thing that's really different between them is that this ionic compound is breaking into its two pieces, whereas the covalent polar stays intact as a molecule. And that's a big difference. They're both dissolving in the water, but one is staying intact as a molecule. So the charges associated with water's polar covalent bonds attract it to ionic compounds and polar molecules. So the negative attracts to the positive on the other one, and vice versa. So we've looked at that in great detail at this point. So we also talked about why nonpolar substances do not dissolve in water. And we considered some hydrophilic interactions and some hydrophobic interactions. And we talked about hydro referring to water, and that hydrophilic meant water loving and hydrophobic meant water hating. And some of you said water fearing, kind of the same thing. So in this image, B, and in image A, we can say that image A is dissolved in water because the molecules are surrounded by water molecules. And in image B, we can say that it's not dissolved in water because there's no water molecules in between the molecules that are interacting, right? They're grouped together and then the waters are staying away from them. So the nonpolar substance doesn't dissolve because there's nothing for the water to be attracted to. The water is more attracted to itself than it is to the nonpolar substance, and so the nonpolar substance just stays with the other nonpolar molecules, and all of the polar water molecules hydrogen bond and stay together. We spoke specifically at the end of your storyboard assignment about how a solvent is something that is able to dissolve other substances. And so water is considered a universal solvent, not just because it dissolves a lot of stuff, but because it is able to dissolve many ionic and polar covalent compounds. And so universal means that it can be applied to all, and more substances dissolve in water than in any other liquid. There are many pros and cons, however, to water's behavior as a universal solvent. So this allows us to ask a really important question, which is, why does solubility matter? Why do we study it? Why did we take some time to look at it and model it? And the pros to water's great abilities as a solvent are that it's really, really important for the molecules of life. All of the molecules that help us live and help other organisms live are soluble in water. So oxygen and carbon dioxide are soluble in water. Oxygen dissolved in water is, of course, what fish depend on. And we will talk about how carbon dioxide gas dissolved in water has really large implications for the health of aquatic ecosystems and also for the interchange of gases with our atmosphere and climate change and some of those pieces. Salt, other electrolytes and minerals are water soluble. These are essential for us to survive. If you don't have enough salt and electrolytes, you're not going to do well, as per the development of Gatorade for athletes to replenish those electrolytes and minerals. And of course, sugars, also in Gatorade, are very important for life, and those are water soluble as well. Some of the cons to things being very soluble is that toxic pollutants, both chemical and biological, are water soluble. And this causes a lot of problems for ecosystems, and it can cause a lot of problems for people. Heavy metals like lead are very dangerous and very water soluble. So if you have lead in your water, you can get lead poisoning. And a lot of the other transition metals are also toxic to us, and they can be dissolved in water, and so that can be really dangerous. Inorganic compounds, so things made out of the nonmetals on the periodic table, stuff like cyanide, other things like that, right, are poisons, and so those are soluble in water, and those can be very dangerous. And then organic compounds, which are also made out of nonmetals, those are often polar and water soluble, and a lot of those have been shown to be carcinogenic and really dangerous. And of course, there's a lot of organic compounds that are perfectly harmless. Sugars are an organic compound. It just depends on the arrangement of the atoms, but all of these things are able to dissolve in water, and so that has some pretty large implications for people. Acids and bases also very soluble and can be very dangerous as well for living things. So let's talk a little bit about what acids and bases are. This is a big piece of understanding a lot of the chemistry that happens when things dissolve in water. So when an acid dissolves in water, it produces an H+. So if you take sulfuric acid and you put it in water, it's going to make this H+ ion, hydrogen ion, and so that ends up having a really specific type of behavior that can be very damaging to cell and tissue structures. Some other examples are like hydrochloric acid, which a lot of us have heard of, carbonic acid, and the word acid comes from the Latin word acidus, that means sharp or sour. And if we look at everyday sources of acids, we can see that we know what acids taste like. We've all tasted a lemon or a tomato or a grape or some milk. Probably, hopefully you haven't tasted a fire ant, but if you have, I bet it tasted horrible. Apples have malic acid, vinegar is just acetic acid, and so we have had some experiences with acids in our everyday lives that are perfectly safe, but other types of acids can be really dangerous. So the more H+ ions there are, the more acidic the solution is, and so potentially the more damaging to cells. The properties of an acid are as follows. They taste sour, they conduct electricity, they're very corrosive, so they break substances down. Many acids corrode fabric or skin or paper, and some acids react really strongly with metals. Those are some of the properties that an acid has. Acids are used for a lot of different things. Acetic acid is vinegar. Citric acid is in lemons and limes and oranges. Lots of sour candies like Lemon Heads and Sour Patch Kids have citric acid. Ascorbic acid is vitamin C, which your body needs to function. It's very important. Sulfuric acid is used in the production of a lot of fertilizers and steel, paints, and plastics. Car batteries are acid-based, so there's a lot of important uses for acids. A base, on the other hand, is sort of the opposite of an acid, and a base is a substance that produces OH minus, that's called hydroxide, when dissolved in water. So this little guy is called hydroxide. I'm just telling you because I'm probably going to call it that accidentally, and you'll be like, what is she talking about? I'm talking about OH minus. So, bases like baking soda or Drano or Comet or bleach all produce OH minus in water. So some chemical names would be sodium hydroxide or potassium hydroxide. And a solution that has an excess of OH minus ions is going to be more basic. People also call bases alkali or alkaline. I don't usually use that term myself, but you could. The properties of bases are that they feel slippery because they are basically breaking down your cell structures, and so they're getting your oily phospholipids out and your skin cells are dissolving. They taste really bitter. They're corrosive. They can conduct electricity like an alkaline battery, right? A base battery. They do not react with metals, which is why you can clean your oven with them. Bases give soaps, ammonia, and many other cleaning products their useful properties that allow you to actually clean stuff with them. And the OH minus ions interact strongly with certain substances like dirt and grease, and so that really allows you to clean things effectively. Chalk and oven cleaner are examples of other products that contain bases, so like sidewalk chalk. So take a minute to think about how do we measure or describe how acidic or basic something is. You can write this down in your notebook for yourself, kind of your thoughts around this. Okay, go ahead and pause the video at this point and draw this pH scale complete with pretty colors into your notes. So you have your acidic things, which are 0 through 7. 7 is really neutral. And then 8 through 14 are alkaline or basic. So pause the video now and draw this into your notes. Did you pause it? Okay, good. So acid-base properties are an essential part of water. And so the pH is a measurement of how acidic or basic a solution is. It ranges from 0 to 14. It can actually go bigger than that. It can be negative and it can be higher than 14, but that's very rare. And acids that are lower than 0 and bases that are higher than 14 are pretty darn dangerous, so we don't encounter them very often. pH less than 7 is acidic. That means there's more H plus than OH minus. pH equal to 7 is neutral, so the H plus is equal to the hydroxide. And pH of greater than 7 is basic, so there's fewer H pluses than there are hydroxides. The pH of pure water is 7. And so most water has other things that are dissolved in it that might make the pH a little higher or a little lower. And that's okay. It's not a big deal. The allowable range for the pH of drinking water is 6.5 to 8.5. So that's a pretty large range relative to the concentration of the ions. The content of drinking water is monitored by the EPA, and there are primary standards to protect the public by limiting the levels of contaminants in drinking water. Contaminants that are limited include microorganisms, disinfectants, disinfection byproducts, inorganic chemicals, organic chemicals, radionuclides, And there's some really specific information about that at the link posted at the bottom. I'll post this on Google Classroom as well. Thank you for taking notes and writing down the stuff in blue and going through this in my absence. It means a lot to me. Have a great day.